Have you ever stopped to think about what electricity actually looks like? I don't mean a spark or a lightning bolt, but the force itself, you know? Well, it turns out electricity creates this incredible, invisible landscape all around us. So today, let's kind of put on our virtual hiking boots and go explore this hidden terrain. So take a look at this. On the left, we've got something you've probably seen before, a topographical map of a mountain, showing elevation with all those contour lines. But on the right, that's a map of electric potential. And just look at them side by side. They're strikingly similar, right? You've got a hill and a valley. And believe me, this is no coincidence. It's actually the key to understanding everything.
So that's the big idea we're running with. What if we can genuinely think about the space around electric charges as a kind of landscape? A landscape with its own altitudes, its own steep cliffs, and its own gentle slopes that literally tell every single charge where to go.
Now, to navigate this landscape, we've got to learn the language. And you know what? It really just comes down to two key ideas, potential and field. So let's break them down. Okay, first up, we have electric potential. You probably know it better as voltage. In our map analogy, this is super simple. Potential is just the altitude. It's a single number telling you how high up you are at any spot. Higher voltage, that just means you're at a higher altitude. That's it.
So what about the electric field? Well, if potential is the height, then the electric field is the slope. But it's a really smart kind of slope. It doesn't just tell you how steep the ground is, it's also like a little arrow that points you in the steepest downhill direction. It's got both strength and direction, which, in physics, makes it a vector.
So let's lock this in. Potential is a scalar. It's just a number, like saying, I'm at 5,000 feet. The electric field, though, is a vector. It's more like a little sign on the trail telling you, hey, the slope right here is super steep, and that way is straight down. See the difference? And here's the really cool part. These two things are tied together by a pretty simple rule we can just call the rule of the slope. The strength of the electric field, E, is basically just how fast the potential, V, changes as you move. So if you have a huge change in altitude over a tiny distance, what do you get? A really steep slope, which means a really strong electric field. And this brings us to the most important rule of this whole landscape. Positive charges always get pushed downhill. The electric field always points from a higher altitude, a higher potential, down to a lower one. It's almost like gravity, but just for positive charges.
All right, so we've got our language of hills and slopes down. Now, let's become map makers and figure out how to actually read these electric maps. Those lines you see drawn all over these maps, they're called equipotential lines. And the name really tells you everything. Equal means equal, and potential, well, potential. They're the exact same thing as contour lines on a hiking map. If you were to walk along any one of these lines, your altitude, your voltage, would stay exactly the same.
Let's start with the simplest landscape you can imagine, a single positive charge. What does it make? A perfect symmetrical hill. The potential, or the altitude, is highest right at the center, and then it just drops off smoothly in all directions. The equipotential lines end up being these perfect circles, just like the contour lines of a volcano. Okay, now let's make things interesting. Let's add a negative charge next to our positive one. This setup is called a dipole, and honestly, this is where the landscape idea just clicks. The positive charge is our big hill, and the negative charge is a deep valley sitting right next to it. The electric field lines literally trace the path a ball would take if it were rolling from the top of that hill right down into the valley. So, what about the space between two charged metal plates, like what you'd find inside a capacitor? Well, in that case, the landscape is a perfectly uniform, constant slope, like a perfectly smooth ramp. The equipotential lines are all evenly spaced and parallel. This means you have a uniform electric field. The slope is exactly the same no matter where you are on that ramp. Now, if you only remember one thing about reading these maps, please make it this. The electric field lines, the ones that show you which way is downhill, they will always, and I mean always, cross the equipotential lines, the contour lines, at a perfect 90-degree angle. That is the golden rule. Okay, so this is all pretty fascinating, right? But you're probably wondering, so what? What's this good for? Well, it turns out that understanding this invisible landscape lets us engineer our world in some pretty amazing ways, from protecting skyscrapers to, believe it or not, saving lives. Let's start with a classic puzzle. Why aren't lightning rods, big flat squares or giant spheres?
Why are they always so sharp and pointy? The answer is hiding in the shape of our electric landscape. So here's the deal. It turns out that on any conductive object, electric charge doesn't spread out nice and evenly. Nope. It likes to bunch up and concentrate on the sharpest points, the places with the teeniest, tiniest radius of curvature. You can see it right here. All those charges are just crowded onto that sharp tip. So what does that mean in our landscape analogy? Well, a sharp point on an object becomes an incredibly steep, jagged mountain peak on our map. The contour lines get packed super close together right there, which means the slope, the electric field, is unbelievably intense right at that tip. And that intense peak is exactly how a lightning rod does its job. First, charge from the ground rushes up the rod and gathers at that super sharp tip. Second, this creates a crazy strong electric field right there. A slope so steep, it literally rips air molecules apart in a process called ionization. And finally, that ionized air becomes a nice, safe path for electricity to flow, letting the charge leak off and preventing a catastrophic lightning strike. But this whole idea isn't just for buildings and thunderstorms. Get this. Your own body has an electric map. The way the cells in your heart fire creates this complex, constantly changing electric landscape. And what's an electrocardiogram, an ECG? It's really just a device that's reading the altitudes, the potentials, of that landscape from the surface of your skin. It lets doctors literally map out the health of your heart. By turning this abstract force into a real, tangible landscape of hills and valleys, we can predict things, we can design things, we can even heal people. It really makes you wonder, if we can learn to see the invisible landscape of electricity, what other unseen forces that shape our world could we learn to visualize next?